Alright, let's pretend that this here is a map of the United States. Got the Pacific Ocean here, got the Atlantic Ocean here. We've got New York over here, Los Angeles, California over here. And let's say, for example, that we have a huge pile of coal, 15,000 tons, somewhere in New York City. And we want to move the entire coal pile to Los Angeles, California. How would you do it? Now there are a lot of different ways you could go from New York to Los Angeles, but let's compare to the obvious ways. One, you could load up the coal in a wheelbarrow and push it. An ordinary wheelbarrow has a capacity of about 6 cubic feet, so moving the entire 15,000 tons of coal across the country would take about 90 to 8,000 trips. Since it takes about 90 days each way to walk across the country from New York to Los Angeles, you're never finishing your lifetime by yourself. You have to hire a whole bunch of helpers. Maybe you rent 98,000 wheelbarrows for the year. The obvious alternative would be one freight train. A typical coal train, it can have up to 120 cars. That's mostly determined by the railroad. Each car holds up to 120 tons of coal, so you can move the entire 15,000 tons of coal from New York to Los Angeles in just one trip. I couldn't find the exact schedule, but I'm pretty sure that would take less than a week. Okay, so moving 15,000 tons of coal from New York to Los Angeles is a pretty big job, so you want a really big tool. What's that got to do with astronomy and telescopes? Well, that should be obvious. The universe is a very large place, and it's all out there in the sky. So you want to see a whole bunch of objects. What if I told you that people have been observing the heavens for thousands of years using the wheelbarrow analogy? Look at this object here. Look at that object here. Point this telescope at that. Point this telescope at this. There are so many objects in the sky, and we've mostly been looking at them one by one by one. The only reason we've learned anything is because we've been doing it for so long, keeping a lot of records. But that is about to change with a new telescope being built, the LSST. LSST stands for Large Synoptic Survey Telescope. Now I will be explaining exactly how large it is, what synoptic means, what survey means, and of course, what exactly is a telescope. Now, in order to understand what makes the LSST so exciting, I'm going to compare three different devices. One, I'm going to compare it to a pocket-sized digital camera, specifically the Pentax Optio W10, but that's just sort of arbitrary because I happen to own one. And then two, I'm going to compare it to a famous telescope, the Hubble Space Telescope, just so you know exactly how the LSST is different. Now, one of the main things that determines what exactly a telescope or digital camera is capable of is the diameter of the primary lens or mirror. Remember, it's this lens or mirror that determines how much light it gathers or how fast it gathers light. Now, my digital camera, its lens is less than an inch in diameter. The reason for that is because it has to be able to fit inside my pocket. Likewise, the Hubble Space Telescope, its primary mirror, is 2.4 meters in diameter. And that's partly because it had to fit inside of the space shuttle's cargo bay. The LSST, it's got its main lens is 8.4 meters in diameter. Now remember, when you double the diameter, you quadruple how fast you gather light. And the reason the LSST can be so big is because obviously it's not pocket-sized, it's not going into space. It's going to be assembled on top of a mountain in Chile, which is the west side of South America. Now, all these large modern telescopes, they you don't have an astronomer peeping through them live like you might expect with a pair of binoculars instead. Really, they're digital cameras. They take pictures, and the astronomers, they look at the data from the pictures. So another obvious way to measure the results that a telescope or digital camera is capable of is how much detail is in the image that you might call resolution. There are more complicated ways to measure resolution, but I'm going to stick with the number of pixels here. So the Pentax Optio W10, it's a consumer level camera, and from a few years ago it's about standard, 6 megapixels. Of course you can get higher now, but this was several years ago I got it. The Hubble Space Telescope is actually pretty complicated because it's got different sensors for different jobs. So it switches to one sensor for this type of object, a different sensor for this type of object. And as near as I can tell, the highest resolution sensor it has is 16 megapixels, which is the advanced camera for surveys. Keep that in mind because I'll be talking about surveys later on when I talk about how these are going to be used. And then the LSST, it's going to be 3.2 billion pixels. That's gigapixels. So we're talking about hundreds of times, well, almost 500 times the amount of detail as my camera is capable of capturing. Another way to look at the amount of information in an image is basically, for each of those pixels, how many bits are you digitizing? I'm calling that the dynamic range. There's probably a better term. Now, more is better, and this is actually very important because if you think about it, in this room, everything's pretty much evenly lit up. But if you think about the night sky, there's really super bright objects like supernovas and the nearby stars like Venus. There's really dark stuff like asteroids and comets. And there's stuff that's really close up in the solar system, and there's stuff that's a billion light years away. So you're looking at such a huge range of stuff out there. So more is better. Now my camera is not designed for astronomy. It's only 8-bit, just like pretty much any other consumer level camera, especially a pocket-sized one. The Hubble Space Telescope, I couldn't find this information. Apparently that HST is really technical and complicated, so I couldn't understand what I was looking at. The LSST is going to be 16 bits. So what that means is, for every pixel, they're going to shoot an image and they're going to get a really good range of bright to dark. Another thing that's important about collecting information about the sky is what wavelengths of light the sensor is going to detect. Now the Pentax Optio W10, like pretty much every single digital camera out there, is sensitive only to visible light. You have to realize it's not a technical instrument. It's designed just to mimic human vision. And just for a numerical reference, visible light is roughly 380 nanometers to 740 nanometers. That's the wavelength of the light. Now the Hubble Space Telescope is all the way from 115 nanometers, which means in ultraviolet, all the way, depending on which source, I found different sources of information, up to maybe 2,500 nanometers. And that would be pretty well into infrared, obviously. Again, this is the reason, there's two reasons it can do this better. Well, one is a technical instrument. You want to see as much as you can get away with. And two, the reason it can do it is because it's got different sensors. So you've got one sensor for this, one sensor for that, and can switch to different sensors depending on what it's trying to see. And then three, the most obvious, it's up in the outer space. It's in low Earth orbit. So it's above the atmosphere. It doesn't have to worry about the ozone layer in the case of the ultraviolet, or water in the case of infrared. Now the LSST, it is on Earth, but at least it's up on top of a mountain. So it's slightly beyond human vision. It's going to go a little bit into ultraviolet and a little bit into infrared. So it sees almost twice as much as what you can see with your eyes. So as you can see, about 320 nanometers to 1,050 nanometers. Now the reason you want to do that, if you understand black body radiation, remember when you have a cool object, it's going to glow just in infrared. And then you heat it up, it'll glow red. You heat it up more, it'll glow blue. And you heat it up really hot, it'll glow ultraviolet. So by looking at all these different spectra, it's going to be able to see a nice big variety of objects that you might not be able to see with your eyeballs at all. Now another part, another way of looking at how these telescopes or digital cameras collect information is how they separate the information. Like in your vision, we have what we call primary colors, red, green, and blue. Now that term primary colors really only applies to human vision. In the case of astronomy and other technical instruments, they call those bands. Like you would say you have a red band or a green band or a blue band or whatever. And the way they separate these is with filters. Now in the case of the Pentax Optical W10, it's got 3, red, green, and blue. That's totally arbitrary except for the fact that human vision has red, green, and blue. And the whole purpose of a digital camera like that is just to mimic human vision. Now another thing to keep in mind though, it takes all 3 at the same time. You take one picture and the sensor is covered with little red filters and green filters and blue filters. So it gets all 3 at the exact same time. Now the telescopes, they do it one at a time. They actually mechanically move the filters in front of the camera and out of the way to switch. So like the Hubble Space Telescope, it might take red for a few hours and then switch and take blue for a few hours and then take green for a few hours or something like that. So it's not quite the same process, but the point is the end result is you can still get an image with all sorts of different information in it. Now the Hubble Space Telescope, I didn't bother to count because it actually depends on which sensor you use. I didn't write down which sensor, but one of the sensors actually has 80 different filters that it can put in front of it. So the Hubble Space Telescope, again, is totally maximized for utility, able to see a huge variety of objects and get a very, high quality information there. Now the LSST, it's got 6 of these. One of them in ultraviolet, roughly speaking, the cutoff sort of ambiguous, and then 2 in visible light, and then 3 in infrared. And the reason for that, you get a good separation, so you can easily tell the difference between like a hot object and a cold object, or a red object versus blue. You want to be able to tell stuff apart. But since each one of these, they're taking turns, if you had 80 different filters on the LSST, it would take, 80 times as long. So you've got to be realistic with your trade-offs there. Now, the main purpose of a telescope or camera or any other optical device like that is to collect a lot of light. I already mentioned that before when I talked about why do you want a telescope that has such a huge diameter mirror? Why not use one with a small mirror? And part of it is because you're looking at the night sky. It's really, really dark. You need to collect a lot of light, which means a long time. Now, my Pentax Optical W10, it's not designed for night shooting at all, and sure as heck is not designed for astronomy. It's mostly for day use. Walk around, take a picture, ooh ah. But the actual exposure time is adjustable for light conditions. I mean, if it's a super bright sunny day, it'll take a picture less than 1,000th of a second long, and at night, it'll take a picture up to 4 seconds long. That's just the limitation built in because of, its pocket-sized camera. Now, the Hubble Space Telescope, it's adjustable for reasons that are more complicated. I've never really worked with it, of course. I'm not an astronomer, but basically, I'm pretty sure if you're taking a picture of something bright, you'd use a shorter exposure. You take a picture of something really, really dark, like a nebula, I guess, you'd use a longer exposure. And if you look at the really bright, pretty exposures of the Hubble Space Telescope, some of them are over 100 hours long. Now, the way these are taken is actually a bit complicated. It's not like one long exposure, 100 hours. Remember, they do like this filter a certain amount of time, they do this filter a certain amount of time, they do this filter a certain amount of time, however many filters. And then for each of those, because the way the Hubble Space Telescope keeps orbiting the Earth, each if it's an officially 50-hour exposure time, it really might be 1,000 30-second exposures or something like that. So the Hubble Space Telescope is very, very capable, but that just means they had to make it really complicated to get it all to work. Now the LSST is much more simple-minded. It's basically a robot. It's going to, any place in the sky, it's just going to take a 15-second exposure and then right away retake that exact same exposure. Now you're probably wondering, why are they stuck with exactly 15 seconds and why shoot the exact same spot twice? Well, when I talk about what exactly is a survey telescope, and what is the LSST going to be used for, what's it going to do, this will make a lot more sense. Keep this number in mind because it's very important. Okay, now to understand why in the world my pocket-sized digital camera, the Hubble telescope, and the LSST are so different, it's important to keep in mind what are they for. Well, the Pentax Optio W10, it's basically like any consumer-level digital camera, it's supposed to mimic human vision. It sees the same kind of light we see, and you can take pictures of night, day, whatever, and it's supposed to look just like you see it there in person. So you're not going to use it at night for astronomy and see something you didn't see in person or anything like that. Likewise, the Hubble Space Telescope. It's a scientific instrument. It was designed to work, up above Earth's atmosphere, so to do stuff that telescopes on the ground couldn't do as well. And it's got several similar missions, but basically it's looking for certain faraway objects, such as black holes. Remember back when the Hubble was launched, I don't even think they officially discovered any black holes at this point. Nowadays, I'm pretty sure they know there's a black hole at the center of every galaxy at least. So knowledge of the universe has changed a bit since then. And I'm not really qualified to elaborate on it, just keep in mind it's got certain missions. Now the LSST is being built with a very different idea in mind. So one is looking right here at the solar system. NEO stands for Near Earth Object. Now that doesn't mean like the moon, it's slightly farther away from that. But if you think about it, the solar system is a very busy place. It's not just 8 planets and a bunch of moons. There's also all sorts of comets and asteroids and so on. And it's possible that some of them are on a collision course with Earth and we don't even know it yet. But these are small objects, maybe just 100 meters in diameter or less. And they don't glow except for, a tiny bit of heat from the sun hitting them and so on. So the Hubble's never going to see anything like that. If the Hubble takes an 100-hour-long exposure and an asteroid cuts in front of its field of view, the Hubble won't notice the difference. So that's where the 15-second exposures come in. When the LSST takes a 15 exposure, retakes the same 15-second exposure, anything in the solar system might be moving fast enough that you can see the difference. This is how a lot of comets or other objects in the solar system are discovered, just by somebody happens to take the same picture twice, like over a couple of nights, and you see something moving. Another, of course, is the mystery of dark energy. I'm not really the expert at that, except the motion of the universe doesn't seem to add up, and they're trying to figure out what's causing it. And then optical transients, this is anything that's changing. One obvious would be like, in the past, decade or so, that astronomers have come up with a way to detect planets orbiting on their stars. Now, one way is like, let's say here's the star, here's the planet cuts in front, it blocks some of the light, so it gets darker. So if you think about it, if the LSST is taking a picture here and then here, it's going to detect this differing brightness from the star. So once the LSST starts running, we might detect a whole bunch of planets throughout this galaxy anyway. And then there's other reasons that an object might change brightness, and well, hopefully we'll be able to determine some of that stuff. And then galactic structure, I'm not really qualified to talk about that at all, but it's on their website. I've got a bibliography at the end of my speech, by the way. So I talked about the LSST and how it's going to do a pair of 15-second exposures. But one thing I didn't mention, it's actually pretty low magnification. It's almost like the same magnification as my digital cam. Well, okay, maybe more than that. It's actually closer to like 30 power, whereas Hubble is more like close to 1,000 power. The point is, the LSST, because it's doing such short exposures by astronomy standards, and it has such low magnification, it's going to do the entire sky in just a few days. So what's it going to do on the next day? It's going to keep going. It'll actually do the entire sky as visible from Chile, which means the southern sky, everything south of the equator basically, twice a week. And it's just going to keep doing that for 10 years. So the plan is that in 10 years, they're going to shoot the entire southern sky 1,000 times. What that basically is going to be is a 10-year time-lapse video of the southern sky. Now I'm not going to get into the details of what they're going to do with all that information. Basically, it's not a picture. Don't think of it as a camera anymore. Think of it as creating a database of objects. That's what they've got. They're going to have a really huge computer with a whole bunch of information on it, and it's just going to store all these different objects, what they look like, where they are, what they do, etc. So, in conclusion, I'm going to just go back to my pile of coal analogy. Like I said, in the past, astronomy, there have been survey telescopes. They have done the entire sky already. I mean, you can go on Google Sky and see the stars. But those were smaller telescopes and so on. And so really, in the past, it's been more like Hubble and other telescopes. It's just collecting a small amount of information at a time, creating pictures. Look at the pretty pictures. Here's the Orion Nebula, here's the Crab Nebula, here's the Bubble Nebula. But now, we're going to have the LSST go through to the entire sky, put all that information in one big database that's going to be easily accessible. So, it's still under construction. In fact, I don't think it's going to start operation until 2023, so it's not going to be done until the year 2033. Go to lsst.org. It's got a lot of good information there. And that's all.